Sometimes when you're given an application, you're not given a whole set of data, you're only given a few key points. Here's a situation where we have a fox population in a contained area in a forest, and often in a predator-prey relationship, the populations vary sinusoidally. For example, let's say these foxes ate a lot of rabbits. Well, if the rabbit population was low, the foxes wouldn't have enough to eat, so the fox population would go down. Well, when the fox population goes down, then the rabbit population is going to go up because there aren't as many foxes to kill them. When the rabbit population goes up, then the fox population is also going to go up because there are more rabbits now to eat. And then they start eating off the rabbits, and pretty soon there aren't enough rabbits to eat, and the fox population goes down again, and so forth. And just keeps cycling, the two going up and down, kind of trailing each other in a sinusoidal fashion. So let's say we have this contained fox population, and at some time, which we're going to call t equals 0, we started recording, the naturalists started to record how many the fox population in that region. And 2.9 years after the population was started to be recorded, notice that the population reached a minimum, because then it started to go back up again. So it got down to a minimum of 200, then it went back up. And then at 5 years after the first population was recorded, notice that it hit a maximum because it got up to 800 and then started to go down. And assuming that the population varies sinusoidally with time, could we make a graph and write an equation for this population? So if we have a graph here, we're going to say that as time varies, what happens to the population? So time is going to be on the x-axis and fox population on the y-axis. And I'm going to quickly draw the graph if it takes you longer than just pause and get caught up. So here's my y-axis with the fox population on it. So this is fox population. My x-axis is going to be time since the records have been kept. So time since records started. Now, we know two key points. We know that, and these, I don't think one wasn't shown on the thing before, but if you look at your fox population problem handout, you'll see this. At 2.9 years, we were at a low of 200, and at 5.1 years, we were at a high of 800 foxes. Now, we talked about before that if you knew from a low point to a high point, you know half of a cycle. So from here to here is a half cycle. And that is 2.2 years if you do 5.1 minus 2.9. Our next low cycle, our next low point would be 2.2 more years. So if we add 2.2 to 5.1, we'd get 7.3. And we'd have our next low point. I should probably stay consistent with my colors here. 7.3. And if we went backwards towards the y-axis here, if we take 2.9 minus 2.2, we'd be at 0.7, and we'd have another high point. And if we went farther, another 2.2, 7.3 plus 2.2, we'd be at 8.5. I'm sorry, 9.5. And we'd be at another high point. And we could keep going, but you can see here we have several cycles now that we can look at. And we know here that we can figure out the parts of the graph. Sinusoidal axis is halfway between 800 and 200, so that would be at 500. So there's our sinusoidal axis. The amplitude would be between 500 and 800, so that's 300. And I think I'm going to have to move my equation here a little farther over. And this is a cosine graph. Phase displacement is, well, our period is 4.4 because half of the period is 2.2, we saw. And so b is equal to 2 pi divided by 4.4, or pi over 2.2. So if you know half a cycle, actually you can go straight to b by saying pi over half of a cycle. Now, since I used a positive amplitude here, I would have to start at a high point, so I could say x minus 0.7 or x minus 5.1. I could also do x minus 5.1. Or if I made this negative 300, I could do x minus 2.9. So there's a number of different ways. Let me see if I can write that so it's a little more legible. There's a number of different ways I could write the equation basically by changing the phase displacement. Once I have this equation, then I can use the equation and the graph to help answer some questions about the fox population. So think about that. If I know the year, I can estimate what the population would be at that year, either by looking at the graph and estimating, or I could do this in my equation. If I know the population, could I estimate at what point in the record keeping it occurred? Now that's a little tougher, and we're going to have to make that the topic of another video. So here's get you started on the fox problem and see what you can do with the rest of the questions on that.